You walk up to a heavy oak door, you grab the handle, and you push.
Right.
It swings open effortlessly. I mean, it feels entirely intuitive. You push forward, it moves forward.
Exactly. Straight line physics.
Right. But mathematically, the second that door starts turning on its hinges, the clean, comforting rules of straight-line physics completely fall apart.
They really do. It's a total shift.
Yeah, you enter this world that is dizzying, a bit rebellious, and entirely defined by circles. So today's deep dive is into the classic physics text, Dynamics of Rotation.
It's a great one.
It really is. We are decoding that hidden world. We're pulling apart the invisible clockwork of how things spin, twist, and turn, and translating those dry physics equations into the everyday mechanics of the world around you.
It really is a necessary shift in perspective, because
Yeah.
when things start moving in circles, our basic intuition about motion just tends to warp.
Oh, totally.
The forces don't point where our straight line instincts tell us they should point,
Hmm.
and the speeds don't add up the way we expect them to. But what this text does so beautifully is take everyday objects, like a swinging door, a sailing boat, a pendulum, and reveals the elegant rules governing their rotation.
But to even start talking about those rules, the text forces us to establish a ground rule.
Yeah.
Like before we can measure how something spins, we have to define exactly what is doing the spinning.
Yes, the rigid body.
Exactly. It introduces this incredibly strict foundational concept called the rigid body.
Which is absolutely crucial. I mean, in dynamics, a body is only considered rigid as long as the forces acting on it do not change the relative positions of its parts.
Okay, so no squishing.
Right, no squishing. Think about it. If you want to calculate the spin of an object, you have to trust that the object isn't stretching or bending while it moves.
Because if it does,
If it deforms, some of that energy you're putting into the spin is being absorbed by the squishing, and the math instantly becomes a nightmare.
the text gives us some very clear, intuitive examples of this. A heavy metal flywheel turning on a shaft, a stone grindstone, a compass needle. Those make perfect sense,
Yeah.
There's solid metal or stone. But it throws a complete curveball.
Oh, the wheelbarrow.
Yes, it points out that a wheelbarrow, even a solid steel wheelbarrow being pushed along a road, is not a rigid body.
It feels like a trick question.
It really does.
Yeah.
If you are listening to this right now and thinking, wait, a wheelbarrow is made of solid steel? How is it not rigid? I had the exact same thought.
Well, materially, the wheelbarrow is solid. But mathematically, mechanically, it is not one rigid body.
Right.
It's two separate rigid bodies interacting with each other. You have the wheel and you have the barrow.
I was trying to visualize this, and it's basically like a folding pocket knife.
Oh, that's a good analogy.
Right. The blade is made of hardened steel. The handle is steel, too. Materially, you couldn't ask for something more rigid.
Yeah.
But as a mechanical system, because the blade moves relative to the handle, it completely fails the physics test for rigidity.
Exactly. The rigidity they're talking about isn't about the material it's made of. It's about maintaining a constant, unchanging shape.
Right. So if the points on the edge of the wheelbarrow's wheel are constantly changing their position relative to the handles as it rolls,
Then the system as a whole isn't rigid.
okay, that makes sense.
But what's fascinating here is how the text applies that exact logic in reverse to things that aren't made of metal or stone at all.
Right. The sailing boat.
Yes, it explicitly states that a sailing boat is considered a rigid body, but only conditionally.
Okay, let's unpack this.
Yeah.
Because that is wild to me.
It's rigid as long as its sails are completely taut under the pressure of the wind.
Canvas fabric. Literally something you could fold up, crumple, and stuff into a duffel bag.
Yeah.
And it becomes mathematically indistinguishable from a solid block of steel.
Yeah.
Just because the wind tension locks its shape into place.
Precisely. The text also mentions a stone being whirled around your head on a string.
Oh, right.
A string is floppy, but as long as that string is pulled straight and tight by the whirling motion, the stone and the string together constitute a single rigid body.
Wow.
Physicists abstract these complex, messy, real-world objects into incredibly simple mathematical models based entirely on tension and relative position.
So as long as the overall shape doesn't warp during the movement, the rigid body math works flawlessly.
Exactly. It's all about relative position.
Okay, so tension makes a floppy sail rigid. That gives us our defined shape.
Mm-hmm.
But knowing a shape is rigid doesn't actually help me figure out, like, how fast the edge of that sail's boom is going to hit me in the head when it swings across the boat.
Right.
How do we actually calculate the speed of something that's just spinning in a circle?
Well,
Because if you are running down track, we just measure the distance you covered over the time it took, feet per second, miles per hour.
right, linear speed.
But when a rigid body turns around a fixed axis, every single particle in that body is just moving in a circle. The object itself isn't traveling anywhere.
And that is the bridge we have to cross, transitioning from linear kinematics to angular kinematics.
Okay.
Since the object is just turning in place, measuring linear distance in miles or feet for the whole object just doesn't make sense. Instead, we measure the angle it sweeps through over time.
Right.
The text introduces this as angular velocity, represented by the Greek letter omega. This is the rate of turning.
Omega, got it.
And alongside it, we have angular acceleration, or alpha, which is the rate at which that turning speeds up or slows down.
I hear the logic, but here's where it gets really interesting for me, because I actually want to push back on the terminology the text uses here. Yeah. Why on earth do physicists insist on measuring this angular velocity in radians?
The radian debate.
Right. Why not just use degrees, or better yet, revolutions per minute, RPMs?
Right.
We see RPMs on our car dashboards every single day.
That's true.
Why complicate things with radians, where one full circle is a messy 2 times pi? It feels like an entirely unnecessary hurdle for anyone trying to learn this.
It's a very fair critique, and honestly, it's the hurdle almost everyone trips over when they first encounter rotational physics.
It's just so unintuitive.
It seems that way. But the radian isn't there to make things complicated. It's actually there to make the physical reality of the math perfectly elegant.
Elegant how?
Let's visualize what a radian actually is. I want you to imagine taking the radius of a wheel like a solid spoke.
Okay, holding a spoke.
Now imagine you could pull that spoke out, turn it into a flexible piece of string, and lay that string along the curved outside edge of the wheel.
Oh, okay.
The angle that string creates from the center of the wheel is exactly 1 radian.
Oh, wow. So a radian isn't just some arbitrary slice of a pie like a degree is.
Not at all.
Because a degree is just a circle chopped into 360 random pieces because, what, ancient Babylonians liked the number 60.
Exactly. The Babylonian degree has 0 physical connection to the actual size of the circle. But a radian is defined purely by the circle's own physical geometry. Because of that direct physical link, the equation to find out how fast a point on the spinning object is physically flying through the air.
Which the text calls tangential speed.
Yeah.
Or V.
Yes, V. That equation becomes incredibly simple. The text gives us the formula. V equals omega times r.
Tangential speed equals angular velocity multiplied by the radius.
Exactly.
So if I'm looking at the example in the text, the rotating drum that is 4 feet in diameter being driven by a strap that travels at 600 feet a minute, we know 600 feet a minute is 10 feet per second. That strap is physically pulling the outside edge of the drum at a linear speed of 10 feet per second.
Right. And because the drum is 4 feet across, its radius is 2 feet.
Okay.
If you were using degrees or RPMs, you'd have to inject a bunch of messy conversion factors, multiplying by pi, dividing by 180 just to figure out the rotation.
Oh, I hate doing that math.
Everyone does. But with radians, the geometry is built in. If linear speed is 10 and the radius is 2, the angular velocity is simply 5 radians per second.
Just 10 divided by 2.
Exactly. It's a clean, direct multiplier.
That does make the math beautiful. It completely removes the translation barrier between linear movement and rotational movement.
It does. And if we connect this to the bigger picture, well, the text points out that when you use these specific geometry-based terms, angular velocity, angular acceleration, the equations match up.
Match up with what?
The equations for uniformly accelerated rotation end up matching the standard linear equations perfectly.
Oh, really?
Yeah. If you know how to calculate a car accelerating down a highway, you automatically know how to calculate a planet accelerating its spin. It's just a one-to-one swap of the symbols.
Wow.
It reveals that the universe uses the exact same underlying rule book for spinning as it does for moving in a straight line.
That geometric mirror is deeply satisfying.
It is.
But it still leaves a huge gap in the physical reality of things. Like, we now know how to describe the spin mathematically, but what actually causes a rigid body to start spinning in the first place?
Ah, the driving force.
Right. If I want to slide a heavy box across the floor, I apply a force. I push it. What is the rotational equivalent of a push?
To find that, we have to look closely at Newton's laws of motion and translate them for rotation. And to do that, the text takes us on a bit of a historical detour into the word moment.
Yes. I absolutely loved this part.
It's fascinating, isn't it?
It is, because when we hear the word moment today, we think exclusively of time. give me a moment, wait a moment.
Right.
But the text explains that in early mechanics, the word moment carried its older original meaning. It meant importance or consequence.
It's a brilliant linguistic clue that we've almost entirely lost. When early physicists and engineers talked about the moment of a force, they weren't talking about how long the force lasted.
No.
They were talking about the importance of that force when trying to generate a rotation around an axis.
Let's go back to that heavy oak door from the beginning.
Let's do it.
If you walk up to a door, press your hand right up against the metal hinges, and push as hard as you can, you are applying a massive amount of physical force.
Huge force.
But the door barely moves. You will completely exhaust yourself trying to open it.
Right.
But if you move your hand 3 feet over to the brass handle at the far edge and push with that exact same amount of force, the door swings wide open with almost zero effort.
That is the perfect illustration of a moment. The physical push, the raw force you generated, didn't change at all between the hinge and the handle.
Same push?
But your distance from the axis of rotation changed dramatically. That extra distance gave your push a greater moment.
It gave it more importance.
Exactly. More consequence in the realm of rotation.
The force is identical, but the turning power is entirely different just because of where it's applied.
And that's why the text warns us not to just think of the moment of a force as some dry, abstract mathematical product where you just multiply force by distance.
Right, it's a physical reality.
Historically, they used that word to conjure a tangible physical idea. They were trying to capture the absolute essence of leverage.
But the text also acknowledges that telling modern students to measure the importance of a force sounds a bit archaic and confusing today,
Definitely.
which is why it formally introduces the modern technical term we use today, torque.
Derived from the Latin torqueo, meaning I twist.
I twist.
Exactly. Torque is the pure measure of turning power. And defining a unit of torque is wonderfully straightforward. A unit torque is simply a unit force acting at a unit distance from the axis.
Which naturally brings us to the messiest, but honestly most amusing part of the text.
Oh boy, the units.
Yes. Because once you define that a torque is a force acting at a distance, you need actual real-world units to measure it.
You do.
And the British engineering systems of the 19th and 20th centuries came up with some truly specific and somewhat chaotic names to figure this all out.
It is definitely a historical unit soup.
That's a good way to put it.
The text lays out the British absolute unit of torque first. In this system, they use the poundal as the absolute unit of force and the foot as the unit of length. So naturally, the absolute unit of torque becomes the poundal foot.
And right there, the text goes out of its way to explicitly warn the reader. Do not confuse the poundal foot with the foot poundal.
A very necessary warning.
Because the foot poundal is the unit used for work or energy. They sound almost identical, and they are both calculated by multiplying a force by a distance. So why are they distinct concepts?
This is a crucial mechanics lesson. It all comes down to direction. Think about the mechanism of what you are actually doing.
Okay.
Work, measured in foot-poundals, involves pushing something in a straight line. You apply a force, and the object moves in the exact same direction as your push.
Like driving a heavy box across a room.
Exactly. Torque, measured in poundal feet, is entirely different. You are applying a force perpendicular to a lever arm to create a twist.
Like pushing down on a wrench to tighten a bolt.
Yes. The force is going down, but the motion is...
It is a circle.
Exactly. One is a parallel push, the other is a perpendicular twist. The math looks similar, but the physical reality is worlds apart.
That makes so much sense. But the text also notes that engineers out in the field building real bridges and engines absolutely hated using poundals.
They did.
They didn't want an absolute unit. They wanted a unit of force that made sense in their hands on a construction site.
Right.
So they operated in what was called the gravitation or engineer's system. They used the pound pull, the actual physical gravitational pull of the earth on a standard weight. That made their practical unit of torque the pound foot.
And this requires a massive point of clarification. One, the text practically begs the reader to internalize.
Oh, the abbreviation thing?
Yes. The difference between the word pound and the abbreviation pound.
Right.
The text insists on writing out pound when referring to a force like the push of your hand or the pull of gravity, and strictly using pound when referring to the amount of mass the actual physical stuff an object is made of.
So what does this all mean? The engineers are using the pound as a unit of force. But to balance Newton's equations, they still need a unit of mass.
They do.
And they invent a unit of mass equivalent to about 32.2 pounds. and they decide, in their infinite wisdom, to name it a slug.
A slug.
A slug. They named a foundational unit of structural engineering after a slow-moving garden creature. Why on earth did they do that?
It sounds absurd to a modern ear, honestly, but mathematically it's incredibly practical.
How so?
Well, the text defines the slug as a practical unit of sluggishness, which is just a wonderful, archaic way of describing inertia, the resistance of an object to being moved.
Sluggishness. I love that.
Think about the math they're trying to balance. Newton's law is force equals mass times acceleration.
Right. F equals ma.
They define their 1-pound force based on the pull of Earth's gravity. But Earth's gravity accelerates objects at about 32.2 feet per second squared.
Ah, I see it. If you push an object with 1 pound of force, and you want your math equation to result in a nice, clean acceleration of exactly 1 foot per second squared,
Exactly.
the mass you're pushing can't just be 1 pound. It has to be exactly 32.2 pounds to balance out the 32.2 acceleration of gravity.
You nailed it. That 32.2-pound mass is the slug. It exists entirely to make the engineers' daily math clean and easy, stripping away the messy decimals while they're working under the specific, constant conditions of Earth's gravity.
That is so clever.
It is. But this raises an important question, you know. It makes you realize how much of our universal physics is actually deeply tied to the specific environment we happen to live in.
Oh, interesting.
The slug only makes mathematical sense because we happen to have evolved on a rock that pulls things downward at 32.2 feet per second squared.
Right.
If human engineers had evolved on Mars, where gravity is much weaker, our standard unit of sluggishness, our fundamental engineering mass, would be a completely different number.
That is incredible. The underlying geometry of the math is absolute, but the specific units we invent to capture it are entirely human. They reflect exactly where we are standing in the universe.
Wonderfully put.
Well, we've covered some incredible ground today. We started by looking at how a sailboat with taut canvas becomes mathematically identical to a solid block of steel, a true rigid body.
The great concept.
We learned how to measure its spin using angular velocity, omega, relying on the physical elegance of the radian to perfectly connect spinning motion to the actual speed of a moving edge.
We did.
We dug into the historical importance of the moment of a force, understanding why a door hinge holds the secret to torque and twisting leverage. And we untangled the bizarre but deeply practical world of poundal feet, foot-poundals, and the 32-pound slug that kept a generation of engineers' math grounded on Earth.
It really does give you a new appreciation for the hidden mechanics of the world. And to leave you with one final thought, there is a brief, almost throwaway section near the end of the text on the geometrical representation of rotational velocities.
Well, what's that about?
It notes that we define the direction of a rotation based on a right-handed perspective. If you look down an axis and the spin is clockwise, that's your vector.
Okay.
And incredibly, you can combine these spinning vectors using the exact same parallelogram laws you use to add simple straight-line forces together.
Wait, you can just add different spins together, like overlapping circles?
Yes. Next time you see a video of a gymnast tumbling in midair, or an Apollo spacecraft rotating to dock in orbit, think about what is actually happening.
Correct.
They aren't just spinning flat like a record on a turntable. They are experiencing simultaneous intersecting rotations across 3 different geometric axes at the exact same time, pitching, rolling, and yawing all at once.
Oh, wow. To the human eye, it just looks like pure, dizzying chaos.
It looks completely unpredictable. But under the hood, the absolute laws of torques, rigid bodies, and moments we talked about today are perfectly combining.
That's wild.
Those twisting vectors simply add together. So I want you to ask yourself, how is the computer on board that spacecraft instantly calculating the intersecting torques of all those rotating slugs to keep them from crashing?
It's mind-blowing.
The math governing a simple spinning top is exactly the same math keeping a tumbling space station perfectly aligned. We can harness that chaos in 3 dimensions at once, and that is something to truly marvel at.
Which means the next time you push open a heavy door or step onto a merry-go-round and feel that wave of rotational dizziness hit you, just remember, your intuition might feel like it's falling apart, but the hidden math holding you there is perfectly, elegantly clean.
Beautifully said.
Thanks for joining us on this deep dive.